today. So another lever that you can pull to improve supply chain profitability is quick response. So quick response means that so there's the concept of lead time. So lead time is the time between when you place an order and when the order arrives. And management of lead time is one of the most difficult and one of the most common things that companies do. Amazon has teams and teams that manage lead time. So lead time is, say, you go on Amazon.com and you place an order, how long before you receive the order, right? I mean, if you have Amazon Prime, you've paid for expedited shipping, you'll get everything within 2 days. So you're paying extra to ensure that your lead time is fixed. In most real life situations, in most business situations, lead times are not fixed because you're ordering very large quantities or you're ordering very specialized materials or equipment or something. So lead time cannot be fixed. So lead time is variable. How you manage variable lead time can lead to extreme either increase or reduction in inventories and costs associated with inventories. So quick response is part of that management of lead time. So so like I said, it's a set of actions that managers can take to reduce lead time. So what we'll do is we'll take an example from the textbook and we'll work from there. So reduced lead times result in improved forecasts again, and you have a multiple benefits. So one of the other things that quick response involves is, so far in all the inventory seasonal inventory models that we've seen, you have been placing a single order. So you have a single selling season for many reasons. So single selling seasons could be because it's actually a seasonal product, like, say, for example, a sweater. A sweater is a seasonal product. An umbrella is a seasonal product, right? So there are many kinds of products that are seasonal products. Flowers for special occasions, they're all seasonal products. So you have seasonal products, you're placing a single order for to sell for the whole season. But what if you didn't have to place just one order for the whole season? What if you could potentially place multiple orders in a season? So we look at the example of placing two orders in a season, and the extension is similar, but usually even for like long seasons, people don't usually place more than two, maybe three orders, even if they have the time, right? So let's look at an example. I'm going to move over to the textbook. I have the online copy of the textbook right here. Inventories. Right. So here is an example. So let's look at the example of Saks Fifth Avenue. Saks Fifth Avenue is a high-end retailer, as you all know. So Saks Fifth Avenue, a high-end department store which purchases cashmere shawls from India and Nepal, and the selling season for cashmere shawls is 14 weeks. Historically, replenishment lead times have been 25 to 30 weeks, which means that once you place an order, the order will arrive. It could take 30 weeks for the order to arrive. So with a 30-week lead time and only a 14-week selling period, it doesn't make sense for Saks Fifth Avenue to place multiple orders in a season. So they usually place a single order for the whole season before the sales begin. So it is difficult for a buyer to make accurate forecast of demand this far in advance because many things change. I mean, maybe cashmere is not in fashion this year, this season, or maybe it is not a very warm winter and people are not buying winter clothes so much and so on. So there are a lot of reasons why there might be variability in demand, and there might be a competing product or another type of something else going on. So you never know. This results in high demand uncertainty, leading the buyer to order either too many or too few shawls each year. That's always going to happen. But the question is, you don't want it to be way too much or way too little. So that's fine. So typically, buyers make accurate forecasts after having observed the sales on first week. So once they notice sales for a week or maybe 2 weeks, they have a much better idea of how a particular product is going to sell for the season. So they get an idea of what are customers looking for. People who usually buy something like this, are they buying it this year or are they not buying it? Is the economy down? So all of those things, they get a much better idea after observing sales for a week or two. So if lead times can be shortened to facilitate the use of actual sales when placing part of the seasonal order, there are significant benefits for the supply chain. So remember that this is a 14-week chain. So 14-week period. So maybe there is some um, um, room to play here, right? So consider situations where manufacturers are able to reduce replenishment lead time to 6 weeks. Now, instead of replenishment lead time being 25 weeks, replenishment lead time is 6 weeks, which means that once Saks Fifth Avenue places an order, it will take 6 weeks for the order to arrive, right? So everything can be done within 6 weeks. Now, the reduction allows the buyer at Saks to break up the entire season's purchase into 2 orders. So this is what they're going to do. First, they're going to place an order for the first uh, sorry, the first order is placed 6 weeks before the sale starts, and they're going to order for half a season, so 7 weeks. So it's a 14-week season, so they're going to order for half a season just for 7 weeks. The first order must be placed with absolutely no data, so everything has to be based. No, we can't say, we're not going to say absolutely no data. They have data from previous seasons, but they don't have data from this season, so they don't know what's happening this time around. But they have data from previous seasons. They do some demand forecasting, like or using one of the techniques that you all learned. But they do demand forecasting, and they're going to place an order for the first 7 weeks, right? Once the season starts, the buyer observes sales for the first week. So they observe the sales for the first week, and they have a much better idea of how this product is going to sell. Once that happens, what the buyer is going to do is they are going to place an order for the second half of the season based up after observing what's happening in the first week. So what this does is it gives them a much better idea of how their cashmere shawls are going to sell in the second half of the season, right? When placing the second order, the buyer can use sales information from the first week to get a much more accurate forecast, right? So that's the example that we are looking at here. But what this does is this makes everything more complicated. So we're going to make we're going to make one simplifying assumption. It's not a really serious simplifying assumption, but it is a simplifying assumption. So let's look at this particular example, right? So the buyer at Saks must define the quantity of cashmere shawls from India and Nepal for the upcoming season. So let's assume that it costs Saks Fifth Avenue $40 to make the shawl and then get it shipped to the United States. Let's say that the sales price for the shawl is $150. Now, after sales of 14 weeks, if the shawl is not sold, it'll be sold at the discount store, at maybe an outlet store and we can salvage $30 each. So you'll always notice that salvage value will always be less than the cost. Salvage value will never be more than the cost, because if salvage value itself is more than the cost, that is, even after the season is done, if you're able to sell it for more than the cost, then, well, you can sell it forever. I mean, then there is no seasonal inventory set. This inventory can be sold at any point in time. It's just that the sales price is different in different parts of the year. That's the only difference. So in seasonal inventories, you'll always notice that the salvage price will always be smaller than the cost of the item, and the sales price will obviously be more than the cost of the item. Now, before the start of the season, the buyer forecasts that weekly demand is normally distributed. So here, notice that this is weekly demand, not demand for the whole season. So in the previous examples that we did with with the seasonal inventory management, whenever we looked at demand, mean, and standard deviation for demand, we were given the mean and standard deviation for demand for the whole season. But here we are given mean and standard deviation for weekly demand and not for the whole season. So all we have to do is just, we know what it is per week. We just have to make it for the whole 7 weeks or 15 weeks, depending upon what we are doing. We're going to compare two ordering policies. The first ordering policy is you place a single order for the whole season, right? We assume that supply lead time is more than 15 weeks. As a result, a single order must be placed at the beginning of the season. So how much does it cost? What is our expected profit going to be if we place a single order? Now, the other thing is what happens if supply lead time is in fact reduced to 6 weeks. As a result, two orders are placed for the season. One to be delivered at the beginning of the season, and the other order to be placed at the end of week 1, which will be delivered at the beginning of week 8. So you place one order for the first 7 weeks and another order for the last 7 weeks of the season. Now, For policy two, so even within policy two, we'll consider two different scenarios. For policy two, we assume that, so this is the assumption that we are making. For policy two, we assume that once the buyer sees the sales for the first week, she is able to forecast demand for the first 7 period accurately. So once she sees what's happening for the first week, she's 100% sure what's going to happen for the first 7 weeks. She's absolutely 100% sure exactly what the sales are going to be for the first 7 weeks. She's not able to predict sales for the second 7 week period, but she's able to predict it for the first 7 week period. All right. In terms of her forecasting ability for second 7 week period, we consider two scenarios, right? One in which the buyer's forecast accuracy does not improve, and another which the buyer's forecast accuracy does improve. So we are saying that by observing data from the first week, she's able to exactly predict what's going to happen in the first 7 weeks. Not only that, there is a potential for her to have a better idea of what's going on in the second half. So we look at both scenarios. One scenario is we have no idea what's going to happen in the second half of the season, and the second scenario where we have a better handle, which means that there is reduced variability, which means the standard deviation of weekly demand now is 15. The standard deviation goes down from 15 to 3 for the second half of the season. So that those are the situations that we are going to look at. So essentially, there are three things that we're looking at. One is single order, right? Single order, everything for the whole season. So we look at that first. The second thing that we're looking at is we are going to place two orders, but for the second half of the season, we have no extra data. Once you notice everything for the first week, you know exactly what's going to happen in the first 7 weeks. But for the second half of the selling season, you don't have any better handle on demand. And the third model is you are placing two orders, but once you notice demand for the first week, you have a much better idea of what's going to happen in the second half of the season. So that is, the average demand stays the same. The average demand will still be 20 shawls a week, but the standard deviation, instead of being 15, is now going to be 3, right? And that's the assumption that we're going to make. Okay. So that's that's the problem that we're looking at. So these are the two ordering policies that we're going to look at. Now, what we know is weekly demand. So all we know is weekly demand. So how do we make it so that we know demand for the whole season? That is simple. So what I'll do is I'll open up. Let me. Okay, I'm going to open up. I'm going to open up. Just a second. Right. So yeah. So this is for your class, right? Right. So I'm sorry. I'm teaching two sections of it. So just wanted to make sure that I should have this. Oh, what's the problem? Okay. Now, this is the data that we have. The reason I opened this up is all the formulas are already typed in here. So the optimal order quantity formula, the expected profit formula is here, the expected understock and the expected overstock and all of that. All the formulas are already here. So I'm just gonna use the same formula. So I'm just gonna do that. So I'm gonna create another sheet within the same thing. I'm gonna call it impact of speed on profitability. I'm just going to say impact of speed. Just going to say impact of speed. Maybe spell it correctly and all of that. Okay, good. Chat is already there. All right, good. This is impact of speed. So let me just copy these formulas over, paste them. So I don't have to rewrite them. Now what I'm going to do is I am going to insert a couple of, maybe one column is enough, one row. So this I'm going to call single order. So this is the scenario where you're placing a single order for the whole season. I'm going to say length of season. Length of season is 14 weeks, right? So mean demand for us. So when you're calculating average demand and standard deviation of demand, this is how you do it. So because if you're placing a single order, you're placing an order for 14 weeks. You know that the average demand is 20 shawls per week. The demand for 14 weeks will be 20 times 14, which will be 280. So that part is simple. So the average demand is 20 per week. Your 14 weeks, 14 times 20 is straightforward. It's a standard deviation that is different. So when you calculate standard deviation, you don't multiply it with the number of weeks, but you multiply it with the square root of the number of weeks. Now, why do we do that? Why the square root and why not just multiply it with 14? And the reason for that is it comes down to, I mean, you must have learned this in your statistics class, that when you have multiple random variables and you're adding multiple random variables, you can, and you're creating one random variable, let's say from 14 different random variables here, because you have 14 different demands for 14 different weeks. You can, the average value of the new random variable, which is the sum of the 14 random variables, you can just add the average value. So it'll be the sum of all the average values, but the standard deviation is not going to be additive. So you cannot directly add the standard deviation. It's the variance. So the variance for the 14-week demand will be the sum of the variances for all the 14 weeks, which means that it's sigma square is equal to 14 times sigma d, and sigma is just square root of 14. So that's where the square root of 14 comes from. So bottom line is, if there are 14 weeks and you all you know is weekly demand, then to calculate the demand for the whole selling season, you have to multiply it with the, calculate the standard deviation of demand for the whole selling season. You have to multiply it with the square root of the length of the season, right? Or length of the time period that you're considering. It doesn't have to be length of the season, the length of the time period. Okay. So the rest is simple. So the cycle service level and all of that. So let's type in all of the data. So my mean demand is going to be 20 per week times 14, and standard deviation of demand is going to be 15 times. So 15 is the standard deviation of weekly demand times the square root of 14. Oops. Yeah, square root of 14. 56.12. That's the standard deviation of demand. So this is my mean weekly demand. This is my standard deviation of weekly demand, right? Now the sales price. So we know that we're going to be selling the item for $150. So selling the shawl for $150. The cost of the shawl is $40. So this includes everything. So there is no after season sales price or anything like that. The salvage value itself is $30, right? That's the, you know what? The after season sales price is $30. There is no holding cost. We are not looking at any holding cost, even though I think it does say something like a holding cost somewhere here. Yeah, I think it says, no, it doesn't say holding cost. That's fine. So there's no holding cost here. So I'm just going to say holding cost is zero. So the salvage value is $30. The sales price is $40. And the sales price is $150 and the cost is $40. So with that, we can calculate the cost of understocking as, so remember, when you say cost of understocking, the cost of understocking is single item. So the value of CU is 110. The value of CO is 10. So given that, we can calculate the critical ratio as 91.67% or 0.1967. So that gives us an order quantity of 357 units. And for that order quantity of 357 units, we have an expected profit of $29,776.38, right? So that's our expected profit. Again, all the formulas are in there. It's the same formula that I typed out couple of weeks ago when we did the formula. So that's why once you have the formula typed up, so you just have to type the formula once. After that, you just use this as a template. All right. So the expected overstock is 2 units. So in case you do end up with an overstock, you expect an overstock of 2 units, and an expected understock is 79. So if you do end up with an understock on an average, what is the understock quantity? That is 79, and that's okay for us because the cost of understocking, overstock is 79 and understock is 2. That is because the cost of understocking is much higher than the cost of overstocking. So it's much more likely that you'll end up with a overstock than an understock. And when you do end up with an overstock, you do end up with a decent number of items, but that's okay. All right. Okay. So let's go with that. So this is what happens when you place a single order. Now, one of the things that we didn't calculate the last go around in the last few examples that we did is the total cost of understocking. So total, so I'll just say cost of understocking. This is the total cost of understocking. Remember, this is the cost of understocking for a single unit. So what is the total cost of understocking? The total cost of understocking is just the cost of understocking times the number of units that you expect to understock back. So that's the cost of understocking. And the cost of overstocking is again the same. So you expect to be overstocked by 10 units, and cost of overstocking is $10, and expect to overstock by $79. The cost of overstocking is so much. So these are dollars. I'm just gonna make them dollars and take. I don't know why I'm doing this, but that's what it's. Okay, so yeah, so you expect to pay $240 of understocking cost and expect to pay $791 of overstocking cost approximately. Right? So that's something, but this is a useful calculation here. That's why we are doing. Now, let's look at the case of placing two orders, right? So remember, even within the case where there are two orders, we are considering two sub cases. The first sub case is where the second. So once you observe demand for the first week, you know everything that's going to happen in the first half of the season, but you don't know you don't have any better data for the second half of the season. So you're saying that what you observe in the first week is only for the first half of the season. It doesn't affect the second half of the season. Or the second sub case that we're going to see for two order cases, what happens if once you notice demand for the first half of the season, you have a much better idea. That is, the average demand stays the same, but the standard deviation of demand now reduces from 15 to 3. So how much?
I just had a quick question. Is the after season sales price always going to be the same as the salvage value?
No. So sometimes you might have a holding cost in a couple of examples that we did, especially with I think with the green thumb. This was an example that the first two problems from the textbook. There could be a holding cost. So that's why in this case, we'll say that the salvage value is the difference between the after season sales price and the holding cost. In this
Okay.
case, there is no holding cost.
And
Okay.
so the problem will tell us what those costs are.
Absolutely. Absolutely. For example, here, let me quickly show you this again. This was an example that we did, I think, a couple of weeks ago. So this was the green thumb example that we did. It says any unsold units at the end of the season will be disposed of in a post-season sale for $50 each, and it costs $20 to hold a unit of inventory for the whole season. So you'll know what the holding cost is.
Okay.
You're able to see my textbook, right?
Yeah.
Okay. So yeah, so you'll know. So it won't. It's not an opaque thing. All the data will be there. All right. Any other questions? No. All right. Again, feel free to chime in whenever you have a question. It's important because you're not the only one who has that question. Right. So let's look at the case of two orders. Oops. Let me click here. There's two orders. I'm going to call it 2 orders, subcase 1. Right. I'm going to call it 2 orders, subcase 1. Let me insert another. Again. Just trying to find a better way of naming this so you don't get confused when you look at it later. So here I'm going to say second half, same as second half of season, same as first half. So that's the scenario that we're looking at. Second half of the season is the same as first half. Then what we'll do is we'll look at a scenario where second half of the season is different from the first half of the season, right? Now, this is where it's important to realize a few things, right? So we looked at the single order policy, calculate. Now, I think my order quantity is slightly different from their order quantity. I think it's off by 1. I think I have 357, they have 358. That is because they rounded the cycle service level to 2 decimal places, so to 0.92 when it's actually 0.9167. So it includes a slightly small value, and also the standard deviation, they just rounded to a single decimal place. We didn't round the standard deviation, we didn't round the cycle service level. So we end up with 357, they end up with 358. It's really not that much of a difference. And even on the exam, if you're off by a single number here or there that you round up instead of round down or something like that, I'm gonna let it slide. It's not so big in the big scheme of things. All right, so 2 order policy. Now because we're ordering 2 orders, we are first placing an order for the first half. We are only going to look at 7 weeks worth of demand. So it'll be 7 times 20. So 140 is the average demand for the first 7 weeks. Standard deviation will be 39.7. So that's the first piece. And then we'll calculate an optimal order quantity, which is 195. Right? So 195 will be the optimal order quantity, and you'll see that in a second. Now notice that the cycle service level, the critical ratio doesn't change, because the cost of overstocking by single unit or the cost of understocking by single unit, that remains the same, because the sales price and all of that has not changed. The only thing that has changed is the length of the selling period here. So the average demand is 195, the optimal order quantity is 195, and the expected profit will be 14,670. Now, at this point, you expect an understock of 56.4 units, and overstock of 56.4 units, and an understock of 1.5. So let's go back to the textbook. Given that the buyer sees the first week demand before placing the second order, we assume that she'll accurately be able to predict sales. So that's the assumption that we're making. First, consider that, so this is the case where we are considering there is no improvement in forecast accuracy. Now, her second order will also take into account any leftover inventory or unmet demand from the first order. So we know that there is an expected overstock of 56.4 units, and there is an expected understock of 1.5 units, which means that after the first seven weeks, you either on an average you'll either end up with about 56.4 units of overstock, or you might understock by 1.5 units. So you have this idea. So your order quantity for the second half is not going to be 195, because remember that we are saying that the second half of the season is the same as the first half, that we don't improve any our forecast accuracy. The order quantity should be the same, because the first half will be 195, the second half will be 195, and everything works that way. But instead of ordering 195 shawls for the second half, you'll actually only be ordering 140.11 shawls on average, right? So that is how much your second order should be. So you're subtracting the overstock and you're adding the understock. So overstock plus understock, that gives you 140.11 shawls. So that's what you're going to do on an average, right? So because you're doing that on an average, when you calculate the total expected profit from the season, you don't just add the $14,670 for the whole season. in this $14,670 for the second half of the seaon, you have included some extra understocking and overstocking costs. So you have not you have included some extra costs here, because you're not going to be you have an idea of exactly what's going to happen in the first 7 weeks. So if you end up with an overstock, you will order less the next time. If you end up with an understock, you'll order more in the second half of the season. You don't know exactly what's going to happen, but after the first week, you know exactly what's going to happen, right? So you don't know what's going to happen at the beginning of the season, but you know exactly what's going to happen for the first 7 weeks after you notice the first week. So if you have an understock, you order more in the second half of the season. If you have an overstock, you order less in the second half of the season. Because of that, you cannot just add the profits from the two half of the seasons directly. You also have to add the cost of understocking and the cost of overstocking, because you have double counted that in this profit, right? So get around that, you get around the cost, you're going to add back the cost as profits, and that will be the total profit, right? So not this. So now the length of the season is just 7. So second half of the season is same as the first half, or no improvement in forecast accuracy. Either way is fine. So let me say no. I'm going to leave it as it was. So length of the season is, so I'm just going to copy the whole thing over again. I'm not going to change much. I'm just going to copy the whole thing over. The only difference now is the length of the season is 7. Right. So length of the season is 7. Because of that, your average is 140, standard deviation is 39.69, but the critical ratio stays the same. So the optimal order quantity, again, notice that it's 194 for us when it was 195 for them. That's fine. It's only off by one number. So the expected profit is 14,699. You'll notice that the expected understock is 1.59, and the expected overstock is 55.99. So on an average, your order quantity is actually going to be 194 minus the overstock plus the understock. So about 140. That's how much your order quantity is going to be approximately. I mean, it's going to be less or more depending upon what you end up with, but that's the average order quantity. So because of that, you can calculate the total cost, total profit. Calculate the total profit as 2 times the 14,699. Again, 2 times this, because you're saying that both halves of the season work the same, but you have a better idea of what's happening in the first half of the season, so you can plan for that. So because of that, you have double counted the cost of overstocking and understocking in the second half of the season. So you're going to add back the cost of understocking and the cost of overstocking as profit values. There you go. So $30,069.69. So that is how much profit you can expect, the average profit that you can expect if you place 2 orders in a season. And the second half of the season works the exact same way as the first half of the season. And so increase in profits, slightly smaller. About $302.31. That's how much more you will make by placing 2 orders in a season. That doesn't seem like a lot, but that's a 1% increase in net profit. That's decent. It's a decent increase, right? Now, you can get rid of that. Now, what happens if the second half of the season works works differently than the first half of the season? So we'll calculate that, but before I go ahead, so again, what we're doing is, instead of looking at a 1 14-length season, you're looking at 2 7-length seasons. So because they work the same, you might say, fine, I'm going to calculate everything for the 1 7-length season, in which case I get a profit of 14,699. And so I'm just going to double it. But you can't just double it, because after observing demand for the first week, you know exactly what's going to happen in the first 7 weeks. Because of that, you can plan and say that I'm going to order more or less than the 194 that I'm supposed to order. And so because we double counted the cost of understocking and overstocking for the second half of the season on an average, we're going to add back the cost of understocking and overstocking. And that's the total profit. Right? Now let's see what happens for the other scenario. So there are three important consequences. One is that the expected total quantity ordered during a season with 2 orders is less. So that's one thing that I wanted to notice. So this is 194. So you're ordering less each time. So which means that you shipping and everything will be much easier. So the average overstock to be disposed of at the end of the season sales, if a follow-up order is also lower, and the profits are higher. So what this essentially says is that, what this essentially means is that at the end of the second half of the season, you will only be left with about, if you end up with an overstock, you'll only be left with about 56 units. But if you place a single order for the season, the expected overstock is 79 units. So the cost of overstocking is much higher for a single order than for multiple orders, right? You're not going to end up with anything at the end of the first half of the season, because you're just going to, if you end up with anything extra, you'll just sell them in the second half of the season. But by the end of the second half, the expected overstock is only 56 units approximately, right? So that makes your life easier. So a number of units that you have to sell at the end, they definitely reduce. Okay. Now, what if the second half of the season you have increased forecast accuracy? So if that's the case, what you're saying is that the standard deviation, instead of being 15, is actually 3. But remember, for the first half of the season, the first 7 weeks, the standard deviation is still 15, because you've not observed sales for the first half of the season. So standard deviation is still 15. So you place an order based upon 15, and the order standard deviation will be 39.7. All of that is fine. So the first order will still be 195 units, 194, depending upon how we do it. The next expected profit and all of that, you can calculate all of that. Expected understock, expected overstock, all of that is good. But for the second half of the season, now instead of standard deviation being 15, it's going to be 3. So what does that look like? So I'm going to say 2 orders. Again, this is the first half. This is the second half. Okay, so let's, so I'm going to again copy the formulas over. It's none of the formulas change. Everything remains exactly the same. So I'm just going to copy the same formulas over again. Now, the first half of the season, it's again, length of the season is 7. The mean demand is 140. Standard deviation is 36.99. So 39.69. So all of this is the same. You're going to order 194 units. The expected profit is that. You're going to be up by, potentially you can be understocked by 2 units or overstocked by 56 units, depending upon which situation occurs. And this is the cost of understocking and overstocking and all of that. That's good. But for the second half of the season, standard deviation is 3. Standard deviation of weekly demand is 3 and not 15. So what that does is, because standard deviation reduced, now your order quantity is going to reduce, because you have a better handle on how much to order, but your profit goes up. Now you'll notice that understock, you don't expect any understock at all. So there's a zero, almost zero understock. The expected overstock is 10, right? So much lower overstock. So by the end of the second half of the season, you expect only about 10 extra units to be left over. You don't expect it to be understocked at all, right? Because you have a much better handle on what your variation is, the standard deviation of demand. So now, just as a calculation, so for the second half of the season, your order quantity on an average is not 150, but you're going to subtract the 56 and add. It's about 96 on an average. So it's the average, not what you actually end up ordering, because what you actually end up ordering depends upon whether you had an understock or an overstock. That's the average order. Anyway, so with this, you can calculate the cost of understocking and calculate the cost of overstocking. And the total profit, calculate the total profit, will be the profit from the first half of the season plus the profit from the second half of the season, plus, again, you're double counting this understocking and overstocking units. So you're going to add the understocking and overstocking cost from the first half of the season, because that's the one that you're double counting, not this. And there you go. It's slightly more. So I can again calculate this number here. This is the difference between. This time the increase is, how much is this? This is about 1%, right? 1.02%, and this is about 2.9%. About 3%. So in the first case, if you just if you don't improve the accuracy for the second half of the season, you increase profit by about 1%. But if you are able to increase the accuracy for the second half of the season, you can improve your profit by almost 3%. That's a significant increase. So again, the only difference here is that we are doubling the 1469 because we are assuming that both half of the seasons work the same. But here, because both half of the seasons work differently, you're going to add the cost from profit from the first half to the profit from the second half, and then add the understocking and overstocking averages, because you have essentially double counted them. And that's it. So that is how you manage scenarios where you could potentially place a second order in a season, in case you have to. Right? Okay. So let me share. I'm just going to save this file. I'm going to post this Excel file on Canvas, obviously. You can see all the different ones. So let me